So when we discussed open addressing, aka linear probing, we basically would start at the insertion index, and if we didn't find an open slot, we would just keep going one by one by one until we found a spot that we could insert. And for find, we would start at the index at which the hash would tell us, and then we would one by one keep iterating if we didn't find the element. As you saw, this could get pretty slow because we could get clumps that would grow as we inserted more elements. And just generally speaking, every insertion will cause the probability of future insertions to become even worse. If I insert something with open addressing or linear probing, regardless of if I had a collision or not, I would definitely be occupying one additional space after the insertion. So there's another collision resolution strategy called closed addressing, which is also called separate chaining. Basically, instead of probing across the other cells of the array, let's just treat every single cell of the array as essentially a linked list. So each cell of the array is a linked list. And then when I do an insertion, if I have a collision, I will just probe down this linked list instead of across the hash table. So let's see this in action. So let's say I want to insert these elements in this order. Their hash values are just their ASCII values. To get indices, I mod by the length of the array. So 65 mod 5 is 0, 67 mod 5 is 2, 70 mod 5 is 0, 71 mod 5 is 1, and 72 mod 5 is 2. Now to insert, let's do the first one. So A maps to index 0, so I just add it to this list. Easy as that. C maps to index 2, so I just add it to this list. Easy. F also maps to index 0. Well, intuitively, I can just add it to this linked list. There's actually a decision that has to be made, though. Basically, given that this list is not empty, F could theoretically already exist in here. So actually, maybe I'll come back to that. So for now, let's just blindly add F as the child, so as the next element in this linked list. G will just insert into this list. H, I'll go to this index, and then I'll insert it right here. So as I mentioned, what if later I tried to reinsert F? Remember, we don't allow duplicates in a hash table. So if I tried to insert F again, theoretically, if I just blindly insert it at the end of this list, I would have a duplicate, which isn't necessarily a good thing because it'll make future lookups potentially slower. So instead of having an F, basically, when I do an insertion, I should first go to that index and check the list to see if the element that I'm trying to insert already exists. So for example, let's try to now insert, so let's see, F, G, H, I, J, K. Let's try to insert K. So H of K, capital K, is 75. And we know that 75 mod 5 is 0. So when I try to insert it, I go to index 0. What I should first do is linearly scan this linked list. That's not K. That's not K. Oh, I've reached the end of my list? Perfect. Now I can add K. So upon insertion, I should look through all of the elements to see if my current element exists. And the reason for this is, what if after this insertion, I tried to insert F, insert F, insert F, insert F? What would happen? If I just blindly inserted it each time, I would get this super, super long chain of Fs going down from the K, which would potentially make my future lookups quite slow. So to keep these lists short, and therefore to keep my performance fast, I should, upon insertion, scan this list and then check, does the element exist? If it does not, now let me just add it to the end of the list. So that's the insert algorithm. To find, it's also quite simple. So let's say I want to look for H. H maps to index 2. I go to index 2, and I just scan this list. C is not equal to H. H is equal to H. Yep, H exists in this hash table. So the reason why this is called closed addressing is because, again, an array, we can think of each cell as being defined as a memory address. And when I do an insertion, any given element will only exist in the slot of the array associated with wherever it ended up based on this hash function. So I'm not allowed to go to any other addresses in my array. I go to this single address, and then from here, I can probe some list. Confusingly, it's also sometimes called open hashing, not to be confused with open addressing. It's called open hashing because we're allowed to store elements outside of the physical hash table itself. So these nodes are just randomly somewhere in memory. So sometimes it's called open hashing, it's called closed addressing, or the most common term is really separate chaining. Let's think about the performance here. Theoretically, I could get super unlucky and every single element could map to the exact same index when I'm inserting. In that case, I'm just doing a bunch of insertions into a linked list. That would make my worst case time complexity for finding an element big O of n. Because I would have a linked list of length n because I'm not using any of the other cells. However, we should hopefully be able to design our hash table and our hash functions such that this does not happen. So in expectation, we expect constant time. With respect to linear probing, let's see what the comparison is. So in linear probing, if I have a collision, that collision will still end up with an extra slot of my array filled, so future insertions will still be slower. With closed addressing, so with separate chaining, if I happen to insert into an empty cell, that's excellent, that's super fast. However, if I get a collision, I'm adding to one of these lists, I'm not filling up any additional cells, so future chances of collisions do not go up. So with linear probing, even a successful, or even with or without collisions, the chance of a future collision would always go up. With separate chaining, if I don't have a collision, the chance of future collisions will go up. I've now filled an additional slot. But if I get unlucky and actually have a collision in this insertion, future insertions do not get more likely to have a collision. The probability of a collision on the next insertion stays exactly the same. One last discussion. You might be thinking, why did I pick to use a linked list? A linked list is such a simple data structure, and it would theoretically make more sense to use like a red-black tree, an AVL tree, or maybe even another hash table. Why not have each of these chains be a separate hash table? And the reason for this is that really a hash table should have close to constant time performance. If your hash table is getting into this big O of n range such that the choice of this separate structure actually makes a difference, you're doing something wrong with the design of your hash table. So here, let's compute the load factor. I've inserted 6 elements into a hash table that has an array of length 5. The load factor is 6 over 5, which is greater than 1. This is terrible. Remember, a good load factor should be roughly 0.75. So I'm making this bad performance because of poor design. If you ever feel the need to do a more sophisticated data structure than a linked list, you're probably not designing your hash table properly.